Hi, I'm Barbara Odegaard. I'll be your teacher for this course. Differential equations, and we're using ZIL. I don't know if you can see that. And so I'm just going to start off today. I assume that you've all read the syllabus and that we're going to work on section 1.1. So just to go through some definitions before we get started. What is a differential equation? So basically, oh look, there's a spelling error already. I don't have any spell check on my system here. So basically, a differential equation is just an equation that contains derivatives. And most commonly, you would see something like dy dx plus 3x equals cosine x. That would be a differential equation. It's got a derivative in there. Or maybe you have second order differential equation. It could equal 0, something like that. Just an equation with derivatives in it. It's ordinary if it's just with respect to x, and so if you just have regular derivatives, not partials in here, we call it an ordinary differential equation. And then it could also be a partial differential equation if you have partials. So for example, y could be a function of x1 and x2, and then you might have something like the partial of y with respect to x1 plus the partial of y with respect to x2 equals 1 or something like that. And that would make it a partial differential equation. So, of course, in math, we start to classify, differential equations. So one thing that when we do is classify them as ordinary or partial. And then the other thing would be to look at the order of the differential equation. And that's simply the order of the highest derivative in the equation. So, for example, back here, this is of order 2. And this would be first order. Other characteristics of linear equations, or of differential equations, would be whether or not they're linear or not nonlinear. And here's the form for linear, right here. And when you look at the form for linear, some things that you might notice is that the coefficients only have x's in them. There are no y's. This should be of x. And then the other thing about this is that we don't have any derivative squared or no y cubed times a derivative, none of that. So this would be nonlinear. That right there, that's a linear term. That's not a problem whatsoever. But if we had something like this, it wouldn't be the sine x that would make it nonlinear, crazy enough. It's the y times the second derivative of y. Or if we had something like derivative of y with respect to x squared. This would be a problem here because this is a power on the derivative. That's going to make it nonlinear. Another thing that would make this one nonlinear is this factor of tan y. You notice over here that this function on the end has to just be a function of x, so no y's over here. And then what we do in this class is we try to solve differential equations. And so we'll be looking at them, trying to recognize them, classifying them into various types, and then applying certain techniques depending on the type to solve them. And by solving them, what I mean is we'll just find the y that works in that equation. Okay, and we always want to find, we're not looking just for y equals 0. Sometimes y equals 0 will work in almost any differential equation, but we're looking for non-trivial solutions usually, unless the trivial solution is all there is. So let's just take a few questions out of section 1.1 of ZIL and see how these go. So let's look at question 2. It says, is this a linear or nonlinear differential equation? Okay, and we can say right away, well, it's nonlinear. When you look at it, major problem right here, we're taking the first derivative and raising it to the 4th power, which this is a nonlinear term in y. So basically when we're talking about is it linear or nonlinear, we're talking about linear in y and its derivatives. There's no problem with this first term here. That's great. And then this, of course, this is the last term right here. That's perfectly good to have that y right there. So that's not a problem, but it was a problem right here. That's what created. This term is what made that whole equation nonlinear. Let's look at number 6. Again, another nonlinear. No problem with the first term, the second derivative of y with respect to x. And no problem with this 9y term. That's perfectly fine. That's just the last term over there on the left. But here was the problem right here, sine y. To be linear, this g of x has to be a function just strictly of x. And this is a function of y right here. So this had problems right there. So this makes that okay. All right, I'll be talking to my computer. All right. Sorry about that. I had a little bit of a interruption. So let's see, nonlinear. Let's look at 8. You can see here that the r is acting like the y, the t is acting like the x. So we have the second derivative is equal to a minus k over r squared. Now this, again, there's no problem over here with this second derivative, but over here we've got a big problem because this is not a function of t or x. Normally we'd say x, but you can see that the independent variable here is t. And so this is nonlinear. Gee, I think, the even ones are starting to look like nonlinear. So let's see. Now here is an interesting one. And maybe this is the first time you've seen this. They've split up the derivative. Isn't that amazing? And so let's go ahead and put it back together again. So I'm going to divide by dx. So we have x dy dx is equal to y squared minus 1. When I move this stuff over to the other side, it'll become y squared minus 1. This will cancel here and here. Now, when you look at that, you could also write it like this. Running out of room. There's no problem with this term. That's linear. But here's the problem. We've got a power of y. Anytime we have a power of y or power of the derivatives of y, or if we have like a tan y over here, it's not going to work. So this is nonlinear. Okay. Interesting enough, if I just look at 9, you notice that it's linear in y, right? Linear and y, there's the third derivative, there's the first derivative. Sine x and cosine x, those coefficients are only functions of x, that's fine. Over here, that's our g of x. G of x is equal to 2, that's perfectly fine. This one's linear. Okay. Now, how do we know when we get a solution to the differential equation? In the beginning, he's going to give us the differential equation and then ask us to just verify that it's a solution. And then, of course, the whole goal of this class is to actually be able for us to come up with the solutions. But let's look at 14. And I might accidentally stumble into a hornet's nest here, but okay. So he claims this is the solution. Here's our solution. Here's the differential equation, and he claims this is the solution to this differential equation. So what I'm going to do is just check and verify to see if it works. So first derivative would be equal to a minus 6/5 times e to the minus 20t times the derivative of the exponents, that would be a negative 20. So the first derivative would be 125ths e to the minus 20t. I'm a little rusty on my differentiation, so you have to watch me. So 5 goes into 120. What do you think? 24 times, huh? And that's the first derivative. So now I'm going to plug that in. So I have a 24 plus 20 times y, and y was 6/5. And I'm wondering if that's equal to 24. I know I'm going to run out of room. That's one thing about differential equations, is they take a lot of room. Let's see, 5, 4, 24, yeah. So we get an identity. So that says that y equals 6/5 minus 6/5 e to the minus 20t is a solution to the DE. By the way, if we were to look at this differential equation, we would notice that it's first order, because the highest derivative I see is of order 1, and it's linear, perfectly linear in y and its derivatives, and it's ordinary, huh? No partials in there. Okay. So that's all we're doing here in the beginning, is just practicing our differentiation. We might also kind of be interested in the interval. You can see that this interval y is defined everywhere for all t. Let's try another one. Let's go for 18. 18 is a different looking differential equation. So we have 2xy dx plus x squared plus 2y dy is equal to 0. And then x squared y plus y squared is equal to c1, where c1 is just some constant. Now, the one thing you might notice here is that this is kind of funny looking. So I'm going to just divide by dx and try to put it back together. weird looking thing. Okay, so we have that. And, I could have took the 2xy over to the other side, but I really kind of, I have the a of x times y form over here. So that's what I'm kind of going for, is I'm going to leave that y right there. But I could bring it over if I wanted. Now, over here, you notice we're going to have to differentiate with respect to x. So we're going to ddx this, and you notice it's going to be implicit differentiation. So when we differentiate with respect to x, it's going to be 2x times y, just using the product rule, plus x squared times dy dx, plus 2y dy dx equals 0. The derivative of a constant with respect to x gives me 0. And I want to solve this for dy dx. So we have 2xy plus x squared plus 2y dy dx is equal to 0. X squared plus 2y dy dx is equal to a negative 2xy. I start to get the feeling like maybe there's an easier way, but now I'm committed, so I'll just keep going. Okay, so there's my dy. And then we're going to plug that into the differential equation. Okay, wow. And we get an identity. So anyway, I thought I would pick that one because it looked a little different. And let's go down here to 21. They're claiming this is the solution. Okay, so that's where C1 and C2, C1 are constants, so C1 is a constant on this. And so this is the differential equation. Now, one thing you might notice about it is it's definitely not linear in y and its derivatives, right? Definitely not linear. And if we're going to plug it in, we're going to plug in y prime, so we're going to need y prime over here. So I guess I'll go ahead and differentiate. So knock down the 2, y times the derivative of y with respect to x. And then differentiate this side with respect to x. The c1 is just going to be out there, 1 plus 0. So we have y prime is c1 over 2y. Okay, so let's just plug in then. Y is 2x times c1 over 2y plus y times c1 over 2y squared. Now I have to somehow hope to get an identity over there, and I might have to make more than one substitution to do that. It looks like the 2's are gone, and so I have c1x over y plus y c1 squared over 4y squared. So y is c1 x over y plus c1 squared over 4y. That doesn't look like an identity, does it? Let's see. 2x y prime. Gotta make sure I copied it down right. Derivative of that, 1, that, y prime 2x times that, y prime squared, y prime squared, that. Okay, so I think what I'm going to do is multiply both sides by 4y. And so we'll get 4c1 plus c1 squared, 4c1x plus c1 squared. And then I'm going to divide by 4. I guess I could have done that a little more elegant. c1x plus c1 squared over 4. And then let's factor out a c1, and we have x plus c1 over 4. Now when we look back, we can see that that's y squared, right? So I'm going to substitute in again, and I get an identity. Wow, that was a little strange too. I'm just looking through here for anything that looks interesting. Let's just try 36. That looks kind of interesting derivatives in there. And then here they claim this is the solution. And then of course they're saying x is greater than or equal to 0, or we couldn't ln x. Okay, so we're going to need, you can see that this is second order. It's second order linear in the y's and the derivatives of y. So second order linear, and it's also ordinary, no partials in there. So looks like we're going to need the derivatives. So y prime would be 1 times the cosine of ln x plus x times, derivative of cosine would be negative sine times the derivative of ln x, which is 1 over x. So the derivative, the first derivative, is looking like cosine ln x minus sine ln x. That's the first derivative. Somehow I have a sneaky feeling I'm going to need more room. The second derivative of cosine would be negative sine ln x times the derivative of ln x. And then minus derivative of sine would be cosine ln x times the derivative of ln x. And so the second derivative looks like negative sine ln x all over x minus cosine ln x all over x. Okay, so we're ready to plug in. So we have x squared times negative sine ln x over x minus the cosine ln x over x minus x times first derivative plus 2 times y. And that's supposed to all equal 0. So we're checking that to make sure that that's true. You can see here when I distribute the x squared through that some of these x's will cancel down here in the denominator. So I'm going to get negative x sine ln x minus x cosine ln x minus x cosine ln x plus x sine ln x plus 2x cosine ln x. And wow, that's going to go with that. And then there's 2 of them. That's going to go. And so 0 equals 0, so it checks. I'm just checking to see what else you have on the assignment here in the 40s. Oh, look at 40. I'll let you do 40. 45. Singular solution for the differential equation. Now, on 45, let's just look at that. And so there's our differential equation. You can see it's nonlinear because it's got a y squared in it. Now, when we look at solutions to differential equations, they break into really two parts. Generally there's a family of solutions. You see, for various constants here, I'll generate different functions, and that creates a family of solutions. So when c equals 1, there's a solution. When c equals 2, there's a solution, and so on. And then also there's the singular solution. Now, the singular solution is a solution that doesn't come from the family. It cannot be obtained by a particular value of c over here out of the family of solutions. It's like a single solution. It doesn't belong to the family of solutions whatsoever. It's a loner. And so they're saying by inspection, determine a singular solution. So find a solution that's not part of this group. Often y equals 0 is a solution, a singular solution. But we're saying, what can we differentiate? And then over here, square it and subtract 1. How about y equal 1? You notice that y equal 1 is not a singular solution, because when c equals 0, we're going to get y equal 1 right here. So it belongs in the family, so I can't call that a singular solution. But I'm looking for a solution over here that doesn't come from the family, but yet it works. And I think if you look at this close enough, y equal minus 1, you can see that there's no way that I can put a value of c in here, the top and the bottom here. These have to be the same number to get a minus 1 out of this. And yet, if y equals minus 1, the first derivative is equal to 0, and if I plug that in, you can see that it works. So this is a singular solution. It's kind of strange, I know. We have a family of solutions here. We have really an infinite number of solutions here for various values of c. And c doesn't just have to be integer. C could be equal to pi, or c could be equal to 0.6, or whatever. But over here, this y equal negative 1 is also a solution, and yet it doesn't belong to this family. You can't figure out a c value that would give you a negative 1 over here for the y, and so that makes it singular. And then the last one is 50. Let's see how hard is that. Okay, let's do 49, and then we'll finish up there. So x squared y double prime minus y equals 0. And they're saying that y equal x to the m is a solution, and we're supposed to figure out the m's that make this work. So y prime would be m x to the m minus 1, just knocking down the power one time. And then the second derivative would be m times m minus 1 x to the m minus 2. And then we're going to substitute that in there. So we have x squared times m minus 1 x to the m minus 2. Oh, I hate it when I run out of room. Let's see. And then minus x to the m is equal to 0. Sorry about that. And then let's just take out the m and the m minus 1. we have x squared times x to the m minus 2 minus x to the m is equal to 0. You notice here that these powers will add. Just like if I had x squared times x cubed, I would get x to the 5th, right? So we have m times m minus 1, x to the m minus x to the m is equal to 0. And I think I'll factor out an x to the m. Remember, there's a 1 there, so that factors out. And x to the m squared minus m minus 1 equals 0. I'm trying to find the m that will make this a true statement. So either x to the m is 0, or m squared minus m minus 1 is 0. Now you can see x to the m equals 0. That's never true, you know. Powers of x, it's only true when x is 0, right? But for in general, to say that x to the m is always 0, I can't find an m that will make that happen. And then over here, you notice I'm not going to be able to factor, so we'll use the quadratic formula. So a is 1, b is minus 1, c is minus 1, and so m is equal to 1 plus or minus the square root b squared minus 4ac over 2 times a. So we have 1 plus or minus the square root of, let's see, that's a 1 plus a 4, that's 5 over 2. So m would be 1 plus root 5 over 2, or 1 minus root 5 over 2. Let's see. Find the values of m such that that is a solution. So, you know, what we're saying is that y equal x to the 1 plus root 5 over 2 is a solution. And then the other one is x to the 1 minus root 5 over 2 is another solution. Okay, so let's stop there, and I'll be posting an assignment for you also on eTudes.